All right, welcome back, everyone. So we're going to continue on talking about the next type of category of relations, which is an equivalence relation. So recall that when we said what we said at the very beginning, we said a equivalence relation is one that is reflexive, transitive, and symmetric, as opposed to anti-symmetric for the partial orders. So what you should know about equivalence relations is that they will have what's called an equivalence class. So let's start with an example here. And this is one that you saw in the in class from last week. There was a relation which is on the set of integers. And or I think the example was on Z plus, but I think both will suffice here. And the relation is AB such that A plus B is even. Right, is an even number. All right, so when you add A and B together, you'll get an even number. So that is that's the relation that we're defining. Now, what you'll find is that as we analyze the relation, reflexive, symmetric, and transitive. Now, you should also note that it is not anti-symmetric, but let's analyze each one of these. So is it true that x plus x, now reflexive means x is always related to itself. Is it true that x plus x is always even? Well, x plus x is 2x, so that's always even, right? No matter what integer I plug in there. So it is reflexive. Is it symmetric? So if I say x plus y is even, does that imply that y plus x is even? Yes, it does. So again, it is a equivalence relation. Sorry, it is a symmetric relation. And what about transitive? Now, this one's a little bit harder to analyze, but if x plus y is an even form and y plus z is an even form, right? So note that that's what I wrote there. Is it true that x plus z is an even form? So if we just add the two, we're going to get x plus 2y plus z is equal to 2k1 plus 2k2. Now, if we move the y over to the other side, hopefully you can see that x plus z is in fact in an even form. So yes, it is also transitive. Another way to state this is that it is impossible to get a non-even number from two sums that are even. So that's another way that you can do that proof. You can do a proof by contradiction. But that's not the point that I want to make here. The point is that it has these three properties, so it is an equivalence relation, right? So if you're asked, is it an equivalence relation? We're going to analyze those three parts. So what is the big deal about equivalence relations? Well, it turns out that because it's symmetric, there's something that we can say in grouping these elements together. Namely, if we grab any of the elements in Z plus, in the set that we're working with, so here we're working with Z plus. So if we grab any of the elements, let's grab the element 1. There is a class of elements that are related to 1 in this relation R. And we denote it by writing something like this. This is called an equivalence class of A. Similarly, we can say this is the equivalence class of 1, which means what is related to 1 in this relation. Okay, so let's pretend that we have a bunch of objects that are related to 1 in this relation. So what plus 1 is even? Well, 1 plus 1 is even. 3 plus 1 is even. 5 plus 1 is even. 7 plus 1 is even, and so on. Now, in a second, we can define what this is, but I want you to see something. Every single element in this relation, in this set Z plus that we're talking about, is going to have an equivalence class. So there's going to be a bunch of objects that are related to it, even if it was just itself. Okay, we'll get to that in 1 second. Now, what is related to 2 in this relation? Well, 2 plus 2 is even, 4 plus 2 is even, 6, 8, and so on. Okay, what about the equivalence class of 3? What's related to 3 in this relation? Well, 1, 3, 5, 7, right? Because those numbers plus 3 are even. Now, I want you to see what comes out of this is that the equivalence class of 3 and the equivalence class of 1 is the same thing. Okay, so one thing that I'll point out right away is that 3 is already found in that equivalence class. Okay, so that tells you something. Okay, what's the equivalence class of 4? Well, it's the same as 2. The equivalence class of 5 is the same as 1. Okay, so what we see is that we can keep going with this pattern. And what we find is that for this whole relation, there are two classes. Okay, there's the class of the odd numbers, and there's the class of the even numbers. So essentially what we're saying here is that any of the odd numbers added together is even. Any of the even numbers added together is even. So there's two classes. Now, if you take a look at the numbers of these two classes, you'll find a couple of things. Number one is that they don't intersect. Okay, there are no numbers that intersect. They are mutually exclusive from each other. In fact, we're going to show later on that if there's even one element in any of the sets that are common, it must be the same set. Okay, so what I mean by that is if you look at the equivalence class of 3, right, there's a 3 in common with 1, right? Right away, you can determine just by that one number, you can say that they have the same equivalence class. They belong to the same class. Okay, so another thing that we should note here is that yes, they are mutually exclusive. Now, does it have to be two sets? Okay, is it true that every relation only has two partitions or two equivalence classes? And the answer is no. You can actually have infinite many equivalence classes. It depends on the relation. In this relation, there are two equivalence classes. Okay, so so that's one thing that we can take out of it. Now, let's move on to another example, which is also an equivalence relation. And hopefully you can see a little bit better how this works. I have an example here, a relation R on the set A, the set of people. And these people are X, Y, and X and Y have the same birth mother. Okay, so X and Y share the same birth mother who gave birth to them. Okay, so so what are the equivalence classes here? And by the way, when we talk about equivalence classes, we also call it a partition. Now, I'll show you why we call it a partition in 1 second. But for now, let's verify that this relation is in fact reflexive, symmetric, and transitive. Okay, is it reflexive? So is it true that X and X have the same birth mother? Well, yeah, because it's the same person, right? Do you and you have the same birth mother? Yes. If X and Y have the same birth mother, does Y and X have the same birth mother? And that's symmetric. So yes, it is. It's true because we have the and here, right? So and the order doesn't matter, right? So if X and Y have the same birth mother, Y and X have the same birth mother. Okay, is it transitive? If X and Y have the same birth mother, Y and Z have the same birth mother, is it X and Z that have the same birth mother? Yes, I believe so. And now we can take a guess, or we can take a look at what is an equivalence class here, right? So let's pretend that we have a person named John. Okay, we have the equivalence class of John in this relation, this R. Okay, so R must have a bunch of objects, so we'll call it A1 all the way up to AN. And who are these people? Well, you might say that these people are John's what? They share the same birth mother as John, so John's siblings. Now, I should also note that John is in there as well. Okay, so just remember, John is also always in the equivalence class of John. It's always in there because it's reflexive. Okay, that's something that we have to note. Okay, now let's pretend that there is another person, Mary, and the equivalence class of Mary contains B1, B2, all the way up to BM. And these are Mary's siblings and Mary herself. Okay. Now the claim is that if I find even one person in that is common to the set A's, the A's and the B's, okay, so if any of the AIs equal the BJs, I hope you understand what I mean by this, right? So any of the A's equal any of the B's, okay, then we can claim that John and Mary are siblings. Okay, so if any of the AIs is equal to BJ, immediately we can say that they're the same. They're the same person. Okay. Otherwise, what can we say? Otherwise, well, the only other way is that there's nothing in common. Otherwise, they are disjoint. So John and Mary have a disjoint equivalence class. So if I take the intersection of John and Mary, their equivalence classes will be empty. All right, now the second part of this statement is pretty obvious, right? If I can't find anything in common, obviously the intersection is going to be an empty set. But the first one is kind of strange because just because I find one element that is in common between the two sets, how is it that I can claim that those two sets are equal to each other? Well, I'm going to prove this in the next slide, but let's just think about it. The answer to that question really is two words. It is transitive and symmetric. Okay, it's transitive and it's symmetric because as soon as I find two people that are the same, right, immediately I know that through transitivity, that AI is related to all the A's. And through transitivity and symmetric, that BJ is related to all the B's. right? So right there, you can claim that those two sets must be each equal. They must be made up of the same elements because they have that that characteristic. Now, if you think about this relation, this is actually a really nice relation to take a look at how equivalence relations behave in terms of a directed graph. So let's say these are the group of people in the world. Okay, so this is the set of all people in the world. Now, what does this relation look like? How does the partition look like? How do the equivalence classes look like in this set? So let's say you have a family of two people. Okay, if you have a family of two people, there's a mother A who gave birth to two kids. Okay, so these two kids are related to each other because they share the same mother, right? So A is related to B because A and B have the same mother, and B and A are related. B and B is also related. A and A is also related. So you can see that if they're in the same family, all the arrows that exist between them will exist. Okay, now let's take a look at another family. Let's say we have another mother who had three kids. So that poor mother who had three kids, let's call them C, D, and E, will again have all the arrows between them. Okay, so C and D, D and E and C, you get the idea, right? As well as these loops. Now, in no way are they connected to A and B because they're a different family, right? But as soon as we find that there is at least one arrow between any two elements, immediately we can say that they're in the same family, right? They're in the same siblings. All right, now you can guess again, if you have four kids, all the arrows exist, right, between them. But can you have an only child? So let's say we have F, who is an only child. So the kid F is now going to be related to himself or herself, but nobody else. Okay, so here's a question, and you can think about it. Can an equivalence class be empty? Can you have an empty equivalence class? Okay, so you can think about it, but the answer is no. You cannot have an equivalence class because what is the smallest equivalence class that we can have? Well, look at F. F is the only child, right? And the equivalence class of F is F itself because it is reflexive, because it's the equivalence relation is reflexive, right? At the very least, F is related to F. There cannot be an equivalence class that's empty. Okay, so keep that in mind. Now, why do we call these partitions? Well, because if you take a look at these, these groups, right, there's actually a partition. You can actually physically draw a line between them, and there's no arrows that are pointing from one part to another part. So that's typically why we call this a partition. Okay, so that's pretty much what you have to know about an equivalence relation. It allows us to be able to take advantage of some of these properties and be able to know that the resulting the resulting relationship or the resulting digraph that we draw is going to have a bunch of groups that are partitioned everywhere. Okay, so let's take a look at a proof of this. All right, so this theorem says let R be an equivalence relation on a set A. Okay, the following statements are equivalent. Now remember, we did a proof like this before. If I wanted to say number one is equivalent to number two and is equivalent to number three, what do we need to do? We need to prove that one implies two, which implies three, which in turn implies number one. Okay, so let's try to do that. I'm going to start at the very beginning and start with A is related to B. Now, the second statement is saying that, now remember, this is a notation that we use. Okay, so this is saying A, B is an element that is found in the relation. So A is related to B in that direction. Okay, so can we then claim that the equivalence class of A is equal to the equivalence class of B? Well, let's see if we can prove that. Can we also say that equivalence class of A intersect with the equivalence class of B is not empty? Okay, so let's see if we can prove all of those things. And in fact, we want to show that, that these things are really saying the same thing. All right, so let's start with A is related to B. If A is related to B, now remember, this is an equivalence relation. So we can also say that B is related to A. Why is that? Well, we'll label this number one and number two. We can say number two because it is symmetric. Okay, we know that it's equivalence relation, so therefore it must be symmetric. Now, let's pretend that C is in the equivalence class of A. So right now I'm trying to derive the second statement. So let's say C is in the equivalence class of A. So what that means is that it must be that A is related to C. Okay, so A is related to C. Oh, by the way, if I say that C is in the equivalence class of A, is it that A is related to C, or is it that C is related to A? So I'll ask that question again. If I say that C is in the equivalence class of A, does it mean that A is related to C, or does it mean that C is related to A? Think about it. Okay, the answer is it doesn't matter, right? Because it's symmetric, it's both, right? So here I'm writing that A is related to C, but in fact, I could have just as easily written that C is related to A. Okay, it made no difference there. Okay, but what it does make a difference in is that we can say C is related to A, but while C is related to A, A is also related to B. So from number one, okay, I'm going forward in the forward direction. From number one, I can say C is related to B. Now, why is it that I can say that? So C is related to A is related to B, C is related to B. It's because it's transitive. Okay, and from this, we can now say that C is in the equivalence class of B. Okay, but after all, we've only said this in one sense, right? So we've only said it in the forward direction. Does the backward direction also work? So does C also allow us to go back? Sorry, equivalence C in the equivalence class of B, does it allow us to go back to the previous statement? The answer is yes. So now C is related to B is related to A. From number two, I can go back and say C is related to A. And then I can go back here and I can go back here. Okay, so what we've shown here is the equivalence class of A must be the same as the equivalence class of B. Any element in the first set is also in the second set and vice versa. So they're equal. Okay, so we've just shown that number one implies number two. Okay, now we have the fact that two sets are equal. Okay, so right now we have the fact that two sets are equal. If I generally tell you that two sets are equal, what can you tell me about their intersection? Okay, well, if two sets are equal, then clearly their intersection cannot be empty unless they're empty, right? So I'll say that one more time. If two sets are equal, their intersection will never be equal unless they're empty, right? So A and B are empty. But here, are the two sets empty? No. So right away, I can claim that the intersection of A and B cannot be empty because these are not empty. They cannot be empty because it's reflexive. Remember earlier in the previous statement, I asked, is it possible for an equivalence class to be empty? No, it's not possible for it to be empty, right? So number two implies number three. It's pretty straightforward. Okay, now since A and B are not empty, it must mean that there is an object K that is in the intersection. Okay, so let K be an element that is in the intersection of these two. Okay, what that would mean is that I can write four statements that are true. K must be related to A must be related to K, B must be related to K, and K must be related to B. So these four statements are all true just because I know that K is in the intersection of the equivalence classes of A and B. Okay, just convince yourself of that, right? So K is related to A, K is also related to B, right? Those are the four things that we can write down for that. All right, so I'm going to grab this statement and I'm going to grab this statement. And through transitive, because of transitivity, I can now say that A is related to B. And this is back where we started from the beginning. So we've shown that number one implies number two, implies number three, which implies number one. And see, when we start our proof and end our proof with the same statement, then we know that every statement is equivalent. Okay, that was one of the techniques that we talked about earlier in the semester. All right, so that was just our definition of partition. So just make sure that you understand that the main concept here is that whenever we have an equivalence relation, the elements that are involved, each element has an equivalence class, and these equivalence classes must be partitioned. They're going to be separated into groups. Okay, so for our final subtopic of this semester, we're going to talk about our growth of functions. So growth of functions is a topic that you're going to see a lot, especially if you're going into computing science. For other faculties, I'm not sure. I'm not quite sure if you're going to do a lot of growth of functions, but it's always something good to know about how functions behave. So the idea is that I want to be able to compare two functions in terms of their growth. Okay, so again, I want to compare two functions in terms of their growth. And let's pretend that we're just graphing these functions and these functions are continuous. What we're interested in is the positive version of these functions. Okay, so I don't care about anything negative. I only care about the positive version of these functions. So what are these functions where x is a positive number? And in fact, what happens to this function when x gets very, very large? Okay, so in effect, we want to be able to analyze how the growth of these functions happen way down the line, right? So way down the number line. When we draw a graph like this, I don't really care about what happens to the function here. I more care about what happens to the function way out here. Okay, when x gets very large, what is happening to this function? Okay, when x approaches infinity, but really gets very large. Okay, so let me give you a few examples. So let's start with the definition. We typically say that f of x is equal to big O of g of x. Or another way we say this is that f of x is in an element of O of g of x. Now, both of these things are equivalent. Okay, so saying one is the same as saying the other. In English, how this is read is f is upper bounded by g. Now, this definition is not that, it doesn't really tell the whole story. Okay, so let me give you a few examples. The official definition here is that if f is upper bounded by g, that means f of x is less than or equal to some constant times g of x for all x that is bigger than some initial starting point. Okay, this is called an initial point. So after some point in the number lines, after some x, anything after this, okay, anything to the right of this, g of x will always be bigger than or equal to f of x as long as we can multiply a constant to it. Okay, so let me give you an example. Let's say, well, the next slide actually gives us an example. So x squared plus 2x plus 1. Okay, so let's say f of x is x squared plus 2x plus 1. Okay, and let's say g of x is x squared. Now, here we can make a claim that x squared plus 2x plus 1 is upper bounded by x squared. Now, if you take a look, if you just kind of remember what you know from math, you might be saying, well, wait a minute, that's not exactly true, because x squared plus 2x plus 1 seems to be a bigger function, a higher function than x squared. But according to our definition, we can multiply a constant to g. So as long as we can multiply a constant to g, we can claim that x squared is an upper bound of the f of x here. So let's take this. So this side is less than or equal to x squared plus 2x squared plus 1x squared. So clearly, this is true, which means that it is less than or equal to 4 times x squared. So here we can report the c as equal to 4, and we can make a claim that x squared is actually upper bounding x squared plus 2x plus 1. Now, let's take a look at the next slide, because the next slide shows you graphically what I'm talking about here. Now, if I just take x squared, then yes, x squared is actually a lower function, is a slower function than x squared plus 2x plus 1. However, if we multiply a 4, then that means it grows faster after the initial point 1. So according to our definition, we can now say that this is true because our c is equal to 4 and our x0 can be equal to 1. Now, in reality, x0 could be anything. It could be 10, it could be 100, right? This will still be a true statement, even if I put 10 here, right? But let's just put 1 because our definition is that for all x that is greater than 1, this is true, okay? So you see, for all x that is greater than 1, this, the green one, is bigger than the blue one. Okay, and that's all we need to show. All right, now you might be asking, well, is it true the other way around? Is it true that x squared is also upper bounded by x squared plus 2x plus 1? The answer is yes. So they are actually upper bounding each other. So the next logical question to ask might be, then what good is this, right? What good is this measurement, right? Where I can say both of them are actually upper bounding each other. Well, the point is that we don't use it in this way, okay? So let me just give you one quick example to show you what I mean by this. Can we say that x squared is upper bounded by x cubed? The answer is yes, we can. Because is it true that x squared is less than or equal to some constant times x cubed for all x, which is bigger than x0? The answer is yes, it is. Even if we just plug a 1 in here and we plug a 1 in here, right, that's a true statement. So x squared is less than or equal to x cubed for all x that is bigger than 1. That's a true statement. So we can say this is true, right? X squared is upper bounded by x cubed. Can we say that x cubed is upper bounded by x squared? And the answer is no, we cannot, because can we find a constant? Now, c is a constant. So can we find a constant so that this is a true statement? No, no c exists for this, right? We cannot find a c that is big enough to make this a true statement. So now you could probably pick out what concept we're talking about here. We are really talking about the class of function, right? So x cubed is a higher class of function than x squared, right? That's really what we're saying here. Okay, so if you want to take a look at the function classes, some of these you probably already know from math, right? But you can see that each of these types of functions grow at a different rate. So log x, actually, let's start with constant. Constant is the slowest growing function, which is flat, right? It just goes flat. So f of x equals 9, f of x equals 10. Anything constant, it will just be flat. Log x is the next slowest growing. It does grow, but very slowly, right? So log of 100 is equal to 2, right? So you can see how slow this function grows. There's a linear function. We can combine functions, so we can do x log x, right? So that grows a little bit faster than x, but not by much. We also have x squared, x cubed, x to the 4, and so on. And the fastest growing type of function is called exponential, which is typically measured in a constant to the power of x. So 2 to the x, 3 to the x, 4 to the x, and so on. Those are the fastest types of functions that we would have. Now, you might be saying, well, what are we going to use these growth of functions for? So it turns out that they can be a very good measurement of the way that we solve problems. Okay, so how do we solve problems in general? Well, we come up with a solution, but before we talk about that, let me go back and talk about a few theorems. So if I have a function f and it's upper bounded by g1, and I have a f2 which is upper bounded by g2. If I sum these functions together, then I'm going to take the max of the upper bounds. Okay, so let's go back to an example that we had before. X squared plus 2x plus 1. We know that this is upper bounded by x squared. Let's take an example like x cubed plus 2x squared. Now you can verify that this is upper bounded by x cubed. Okay, and this is usually where we put our function classes. Okay, so if we add these two together, so if we add x squared plus 2x plus 1, and we add it with x cubed plus 2x plus 2, then the resulting big O, the resulting upper bound, is going to be the max of these two things. Now the max here would be x cubed. So we would say this resulting function is upper bounded by x cubed. This must be true. And again, you can verify it doing an example. Okay, so just verify that this is actually true. Okay, theorem 2 says if f1 is upper bounded by g1 and f2 is upper bounded by g2, then multiplying these two functions together, we must multiply the big O's together. So if instead we do x squared plus 2x plus 1 multiplied by x cubed plus 2x plus 2 x squared, then this is equal to big O of x cubed times x squared, which is going to give me x to the 5. Now, again, you can verify this because if you do FOIL on this function, you're going to get something that is dominated by an x5 term, right? So, so even if we do another example, like if we put a 2x in here, right? And if we had 2x squared times plus 2x plus 1, and then I times the x cubed plus 2x plus 2x squared, then it is still upper bounded by x to the 5. So please, according to the definition that we have, please verify that this is true. Okay. Now, this is not the point that I want to make. The point I want to make is what is this used for generally? Okay. Let me give you an example of a type of problem that we solve in computer science. This problem is called searching. Okay, the searching problem goes like this. If I have a bunch of numbers and these numbers are somehow organized, and let's say I have these numbers 1, 3, 5, 10, 21, 25, 29, and 32. Okay, so let's say I had these numbers and I'm looking for a specific number. Let's say I'm looking for the number 29. Okay, this is called my target. So how much work, how much comparisons do I have to make in order to find 29? Now, there are two ways to answer this question. Number one is what we call a linear search. Linear search means I'm just going to go from the beginning of this list and I'm going to compare the number 29 one by one because there's no telling where it could be. Now, if obviously you're looking at this and you're saying, yeah, 29 is there. But let's say I hide this list from you. Okay, and the only thing you can do is compare 29 with every one of these numbers. So a linear search would say, I'm going to compare 29 with 1, then with 3, then with 5, then with 10, and so on. And so the number of comparisons, the amount of work that we need to do is going to be 1, 2, 3, 4, 5, 6, 7. It's going to be 7 amount of work. Now let's pretend that there are actually n elements in this list. Okay, let's pretend there are n elements in this list. So the worst case in this scenario, so if we take a look at this list, the worst possible case is if I'm looking for a number like 32, or if I'm looking for a number that doesn't even exist. Okay, so if I'm looking for the number number 7 in this list, well, number 7 is not there, right? I'm going to have to search through all of these, all 8 of these numbers in order for me to determine that 7 is not even there. Okay, now how we measure this is in the worst case, when there are n elements, we're going to have to make n comparisons. And the way that I'm going to measure this algorithm, this way that I'm going to solve this problem is to say that you're going to be doing in the order of n comparisons. So no matter how many you do, how many comparisons you do, how much work you do, you're going to do something that is less than or equal to n. Okay, rewind that if that didn't make sense to you. Okay, so again, I'm going to call this function an n, a big O of n function because it does at most n amount of work in order to find this key, this x. Okay, now let's contrast this with another algorithm called a binary search. Binary search does something a little bit smarter. It goes to roughly the middle. Okay, so roughly the middle. I'm going to say roughly the middle is 21. Okay, I'm going to compare 21 with 29. The fortunate thing about this list is that this list is already sorted. Okay, now linear search is going to work all the time, but a binary search will only work if the list is sorted from smallest to biggest or from biggest to smallest. Right, you see it goes up in a progressive manner. So 21 is actually smaller than 29. So I'm going to determine, my algorithm is going to say that, okay, since 21 is less than 29, if 29 is there at all, I need to continue my search to the left, to the right-hand side of this list. Okay, so now my search becomes only 3 elements. Okay, again, I'm going to take roughly the middle, and I found 29. So after 2 comparisons, after 2 amount of work, I found it. Right? Now, what I'm going to tell you is that I'm not going to show you like the full analysis of this, but in the worst case, in this case, with the 8 elements, I will need to find, I will need to make a comparison of 3. In the worst possible case, actually, I'm sorry, not 3, 4. In fact, I'm going to write 3 plus 1. You're going to see why I put that in 1 second. All right. The reason being that I cut the list in half and in half and in half again. And just in case we are we reach the last level, I will need to make one last comparison just to claim that it's not there at all. Okay, so so you can kind of draw a small a small diagram to see how many comparisons you'll need to make for every one of these numbers. It turns out that at least in this case, if I'm searching for the number 1, it's going to take the most number of comparisons. Okay, but what can we say about the worst case? Well, it turns out that this is equal to log base 2 of n. Okay, now I'm not going to get into the reason why this is log base 2 of n, but you can definitely tell that this is a smaller or a faster algorithm than O of n, than linear, because I'm not searching through every item. What I'm doing is I'm cutting things in half and in half and in half and in half. And it turns out that the work that we do is proportional to 2 So it's proportional to 2 times the, sorry, n. So n is proportional to 2 to the work. Okay, without getting into the details of how this works, because we're kind of cutting things in half every time. Now here, if you solve for work, you're going to log both sides. Right, so I log both sides and I move work, the variable work, to the front, and then I can say this is log n over log 2 is proportional to my work. So how much work do I have to do in the binary search? I have to do log base 2n of the work. Okay, let's graph both of these functions. So log base 2 of n is going to look something like this. O of n, so this is log base 2 of n. O of n is kind of going to look like this. So this is the amount of work that we do. So how much work would you like to do? Would you like to do a linear amount of work, or would you like to do a log amount of work? And I think the answer is I want to do a log amount of work because that's the lesser of the two. Okay, so this is how we argue. Whenever we solve a problem in computer science or even other mathematics or whatever, we're going to analyze how good this problem solving method is. We're going to analyze how much work do we do. Okay, now work is going to depend on the type of problem that we're solving, but how much work do we do? Does this algorithm do more work or less work than another algorithm? If another algorithm does less work, that's the better one. Okay, that's in the end, that is what the big O notation, that is what dominance is trying to solve. All right, so I think this is good. I think we're going to leave it there. And again, the point of the big O notation is to be able to analyze the relativity of two functions. And usually these functions involve measuring how much work we do for a given problem that we've solved. All right. Okay, so I'm going to stop the video here.